All right, let's finish up this problem number 2. This is part C. Remember, part A and B we've already figured out. Those were in the in the X-ray, as we're going to see here. This one's going to. So here let me just do this. So 2.9 times 10 to the minus third. Because we don't really want this to be in millimeters. We want it to be in meters. Divided by the temperature right below the surface of the sun, right below the photosphere, is 10,000. So you divide by 10 to the fourth, and you get 290. Well, here's what you get 2.9 times 10 to the minus seventh, and then here's a conversion. I didn't actually do this out in the other two, but this is basically the same thing. So in 1 nanometer, there are 10 to the minus ninth meters, right? So to convert meters to nanometers, right, the meters cancel, right? There's the meters. And so you take this number and you divide by 10 to the minus ninth. So you put this in your calculator, 2.9 times 10 to the minus seventh divided by 1 times 10 to the minus ninth. Remember to use the EE button or the EXP button, depending on what type of calculator you have. Remember, you're never hitting times, you're never hitting 10. All right, anyhow, you get 290 nanometers. And this 290 nanometers happens to be in the ultraviolet range. All right, so the other two were in the X-ray range. This one's in the ultraviolet. All right, so all right, for number 3, they give us the following. The largest amplitude solar pressure wave, a sound wave basically, on the surface of the sun, has a period of about 5 minutes, right? So we've written that right here. It moves at a speed in the outer layers of the sun roughly 10 kilometers per second. So that's supposed to be a 10. So 10 kilometers per second. Part A. How far does this wave move during one wave period? Okay, so during this amount of time, during a time of 5 minutes. Of course, you're going to have to change that to seconds, and so in 1 minute there's 60 seconds, so the minutes cancel, right? And the minutes are canceling, and so 5 times 60, 300 seconds. And so we have this basic equation: velocity is distance divided by time, as long as there's no acceleration. That's always true. And so you rearrange that equation with algebra, very simple algebra. We just multiply both sides by t, so the distance is equal to, in this case, the period, which is 300 seconds, times the velocity, which was given to us as 10 kilometers per second. So 300 times 10 kilometers per second, of course, gives us a distance. So this was part A, by the way. Gives us a distance of 3,000 kilometers. All right, so that's our first part. The second one, part B, says approximately how many wavelengths are needed to completely encircle the sun's equator. And then part C, compare the wave's period with the orbital period of an object moving just above the solar photosphere. I'll do that problem in just a second. Let me pause it. All right, so we're going to do part B of this problem. So we learned before from part A that the distance that one of these pressure waves travels is in 5 minutes was roughly 3,000 kilometers. And in this one, they say, okay, what's let's see, where am I? Approximately how many wavelengths are needed to completely encircle the sun's equator? Okay, so at the sun's equator, the radius, okay, the radius is 696,340 kilometers. And if you have a circle, just to remind ourselves, some basic geometry here. So this is supposed to be, I didn't make that in the center, sorry. So if you have a circle, any circle at all, and you go from the center to the edge, and of course that's of course called the radius. There's a relationship between and it's right here, the circumference divided by the diameter, which is 2 times the radius, is always equal to a constant that we call pi. Right, so we can figure out the circumference, and so I did that here. It's just 2 pi times the radius at the equator. You get approximately 4.38, 4.4, it's fine too, million kilometers, or times 10 to the 6 kilometers. And then what it says, let's see, let me read this, approximately how many wavelengths are needed to complete one of these. And so it turns out that one wavelength, that's the distance that we found before, was 3,000, right? So 3,000 kilometers. So we just take this number right here and we divide by 3,000, all right? This is just to complete 3,000 kilometers, and the kilometers cancel, and so this is the number of wavelengths that would fit around the circumference of the sun, would be 1,458.4 roughly, 0.4 wavelengths, right? So these are, of course, waves that are going around the circumference of the sun at the equator, and so there'd be, more than 1,400 of them, okay? So the next part, let's see, compare the wave period to the orbital period of an object moving just above the solar photosphere. All right, so we first have to figure out the orbital velocity. All right, so this is from chapter 2. I know we didn't cover chapter 2, but this is the orbital velocity. To keep something in orbit, actually Isaac Newton came up with this formula. It's the square root of a constant, it's called the universal gravitational constant, times the mass of the object divided by the distance from that object. And in this case, since it's right above the surface, we're going, R has to be in meters, by the way, so we're going to use the number that we used before, 696,340, but we changed it into meters times 10 to the third. There's the universal constant, the universal gravitational constant, and there's, of course, the mass of the sun. So this becomes 437,690 or so meters per second. So let's change that, of course, to kilometers per second, because that's what we want. So it's approximately 437, I don't know, let's just say 0.7, that's perfectly fine, 0.7 kilometers per second, okay? So we're comparing that, and let me get back to the problem. All right, for this problem, again, these are some things that we had not done in class yet. So the orbital speed, you use this formula to calculate it. The reason that we need the orbital speed is to get what's called the orbital period. All right, so just above the surface of the sun, the orbital period, so I'm using that as T sun, would be 2 pi times the radius at that distance. So this is, at the equator of the sun, divided by the orbital speed. So we know the orbital speed, and we know the radius of course, in kilometers. So we're going to put those numbers in. All right, so again, we're trying to figure out the orbital period. The orbital period is the distance around the circumference divided by the orbital speed, right? Which the orbital speed in kilometers per second would be 437.7 kilometers per second. So you take this, which, 2 pi times the radius in kilometers divided by that number, you get almost 10,000 seconds. Okay, so then the next thing, so what the problem actually says is compare the wave period. So we know the wave period, remember that was 300 seconds, or 5 minutes, to the orbital period of an object moving around, moving just above the face of the sun. All right, so again, it was almost. So this is the period of the sun divided by the period of the wave. All right, so this was it's about 10,000. It's like 999. I don't know. Anyhow, yeah, 10,000, let's see, is it 10,000? No, it's, yeah, it's just under 10,000, like 999, 9,995.9, something like that, divided by 300 seconds, so approximately 300 seconds. And so that comes out to be about 33.3. All right, so that answers part C. I know that's a lot of stuff that we hadn't really done before. All right, let's do problem. All right, let's do problem number 4. The main one, the main issue, or not issue, but the main equation that we're using is velocity is distance divided by time, and they give us a velocity of 1 kilometer per second. Let me read this problem first. It says if convected solar material moves at 1 kilometer per second, how long does it take it to flow across a 100 kilometer expanse of a typical granule? Compare your answer to with the roughly 10-minute lifetime observed for most solar granules, right? So, all right, so the way that we do this is we take this equation, v equals d over t. That's just this normal velocity, no acceleration. Let's algebraically rewrite it as t. So solving for t. So we multiply both sides by t, divide both sides by v. You get t is equal to d over v. All right, so t is d over v, and they gave us. Let's see. So what did they give us? They gave us that. The distance is 1,000 kilometers, so 1,000 kilometers, so that's our distance, and they give us a velocity of 1 kilometer per second, that's a k, per second, and so the kilometers cancel, and so the seconds go up to the numerator, so it's 1,000 seconds. So it takes this thing 1,000 seconds. But you might wonder how much time that is in something that we can think about in our heads. So there's of course 60 seconds in 1 minute. Right. Remember to use MIN for minute. Reserve lowercase m for meter. All right. So anyhow, when you do that, you get about 16.7 minutes. All right. So 16.7 minutes. All right, and then we're comparing. Let me read the rest of it. Compare your answer with roughly 10-minute time observed for most. So in other words, if it's going to go 1,000 meters or 1,000 kilometers traveling at this speed at 1 kilometer per second, it would take about 16.7 minutes. But then what they're saying is when we compare the value to the value that we would find when that is observed in one of these granules, the granules only live for roughly 10, on average 10 minutes, right? So they're not living long enough to cross this distance, because of course it would take them roughly 16.7 seconds. All right, we won't have enough time to finish this. I only have about a minute left, but I'll pick it up in the next video. So let me read this one. It says, use the Stefan-Boltzmann law, that of course the flux is proportional to t to the fourth, to calculate how much less energy as a fraction emitted per unit area of the 4,500 Kelvin sunspot than from the surrounding 5,800 photosphere. So the basic idea, here's the Stefan-Boltzmann law, the sigmas cancel, and so you just take 4,500 raised to the fourth divided by 5,800 raised to the fourth. All right, so for this one, you got to raise these things to the fourth power. You get a fraction of 0.36. All right, so when you solve this, you find that the sunspot flux is only 36% the flux of the photosphere. That's the idea. all right? 0.36, of course, is 36%.